Let's talk about energy. But first of all, we're going to talk about negative work and what that means. So I wrote here, in general, a force in the same direction as the motion. If the motion is this way, F1, which is in the same direction as the motion, that does positive work. F2, we would say that does negative work because it's in the opposite direction of motion. Now, I've told you, Eric, that work is a scalar. It has no direction. It's not a vector. So what does negative work really mean? We're going to talk about that more today, but we need to build some more vocabulary. We talk about energy. Energy is defined as the ability to do work. And since work is force times distance, what we're really saying, Acacia, is if an object has energy, it can apply a force over a distance. It has the ability to do work. There are many types of energy. One of the most common ones that we'll be looking at quite a bit is the energy of motion. We call that kinetic energy. K-I-N-E-T-I-C. If an object is moving and it hits you, can it apply a force over a distance? Does it have the ability to do work? Yes. What else? Heat. Heat is generally created by friction. I'm sure you've all noticed if you rub your hands together really fast, you can generate heat, friction. The next one has two words, gravitational potential energy. The word potential energy just means stored energy. So gravitational potential energy is stored energy due to an object's height. If I lift something up and if I drop it on someone's head, will it apply a force over a distance? Will it do work? It must have had some energy. You store it by lifting it up, and then usually it turns into kinetic energy, the energy of motion as it falls. There's also chemical potential energy. Zaina, what does potential mean? So chemical stored energy, gunpowder is a good example. The food that you eat is chemical potential energy. That's how your bodies get energy. It was originally stored in the food that you ate. There's also other forms. Sound is a form of energy. There's something we call elastic energy. When you stretch something and the molecules want to return to their original shape, you're actually doing force times distance. When you stretch it, you're doing work on the object, storing energy in the rubber band or in the elastic. There's nuclear energy. That's the energy stored inside the nucleus of an atom. Many others. But in this course, we're going to look at mechanical energy. And we're going to break that down into two main types. Kinetic, the energy of motion, and stored, potential. And you can put next to potential, usually grav period. What do you think grav period is an abbrev for? Gravitational. So almost always we'll be storing the energy potentially by lifting something. Not always. If the object is moved horizontally by, well, let's look at some examples. But what this does, Eric, it explains negative work. When you do negative work on an object, what this really means is the object is losing energy. It's losing energy. Pause for a second. Let's do that again. Pick your pencils up. Potential energy. What was potential another word for, Zaina? Start with the letter S. Stored. So potential energy is stored energy. Gravitational potential energy is stored energy by lifting. There are many ways, though, to store energy. A classic one, I like example one, I like example one, I like example one. Example one is a nice question. A classic one is either a bow and arrow system or a slingshot and rock system. In both of them, Cohen, you're applying a force over a distance. You're doing work. So example one says, suppose it takes 250 newtons of force to pull an arrow back 0.78 meters. How many joules of energy are stored in the bow? Well, work is force times distance. Mika, how many newtons of force are we applying in example 1? And over what distance? And they're in the same direction. How much energy have we stored in the bow? What'd you get? Okay. Aiden, what'd you get? See, you're reaching for your calculator now. Cohen figured out I'm coming to him next. Eric, what'd you get? 195? Anybody else? Is that right? 195. Oh, what are the units for work? Joules. When you let go of the string, what happens to all that stored energy? It's transformed. And it's transformed into the energy of motion. It gets transferred to the arrow, and it gets turned into kinetic energy. It turns into kinetic energy. Put your pencils down and look up. So a slingshot, whether it's human or whether it's just one you hold in your hand or a bow and arrow, they are great examples of stored energy. But now we want to talk about a very specific type of energy. So when you stretch a rubber band, you're storing potential energy. A battery, this battery has stored potential energy. It's stored electric potential energy. But the stored energy that we want to talk about now is gravitational. Potential energy. This is the work that you have to do against gravity in order to change an object's height. I had a student earlier today mention that they were feeling a little tired, so we're going to wake them up. So the equation for potential energy is this. I'm going to suggest on your green sheet, put a little g as a subscript so you know that's the gravitational one. That's not all potential energy. All potential energy is force times distance. It's work. But against gravity, it's mgh. Or if you know the weight, it's the force of gravity times height. Because Fg is the obvious one, mg. So Jaden has a mass of 75 kilograms. First of all, what's his weight? Isn't his weight 75 kilograms? No, weight's not kilo. Well, what do I measure weight in? Sorry? Newton. Oh, weight is mg. So this is really saying find the force of gravity. It's going to be 75 times 9.8. 75 times 10 will be 750, so it's going to be 750 take away 15. Is it 735, I think? No? Yes? So Jaden is feeling gravity pulling down on him with 735 newtons. Jaden's got some pretty good hops. He can jump. When he jumps, he can raise his center of mass 75 centimeters. Nice try, Dewick. I don't do physics with centimeters. How do I convert that to meters? Divided by 1,000? Is centi 1,000? I think centi is 100. It's 10 to the negative 2. Negative means you're dividing. So I think it's 0.75 meters. Which one is 1,000, by the way? Starts with the letter K. Someone needs to learn his metric prefixes. You're born in Canada. Kilo is 1,000. Okay? At the top of his jump, how much potential energy does he possess? So we're going to find the potential energy, the gravitational potential energy. That's going to be mgh. Instead of going 75 times 9.8, I'm just going to drop the 735 down times 0.75, because that way you can use your answer button times 0.75. How much energy has he stored in his body at the top of his jump? Clothy, what'd you get? 551? 551.25? And then there's a follow-up question. It asks, where did that energy come from? Had to come from somewhere. Where did it come from? Energy came from the food that he ate. Every time you jump, every time you do any kind of physical activity, you're taking some of that stored chemical food energy that your body has processed and you're turning it into work. This is why if you're not eating right, you feel lethargic. You feel tired. Your body is telling you, I haven't got the stored energy resources that you're used to. You might even almost feel shaky. Your body is saying, hey, don't try your normal stuff. I haven't got it for you right now. Is that okay? Ooh. How much gravitational PE, by the way, my abbrev for potential energy is going to be PE, my abbrev for kinetic energy is going to be KE. How much gravitational potential energy does an object have if it's sitting on the ground? Be obvious. 0. And what that also is saying is if you leave it sitting on the ground, it'll just stay there. It doesn't have any energy to move on its own. It can't do any useful work. And then Zaina has anticipated we're going to turn the page. Or no, is it next page over? It's just next page over. Who remembers kinetic energy is the energy of motion? Let's see if we can derive the equation for kinetic energy in the same way we derived the equation for potential gravitational energy. Emilio, what is the equation for kinetic energy?
mv squared.
A half mv squared. V what? V what? Squared. V what?
Squared.
Everybody, V what? Everybody, V what?
Squared.
Everybody, V what?
Squared.
There, I got Mika on board finally too, but I didn't get Cole on board. Everybody, V what?
Squared.
Squared. That squared there, believe it or not, dominates your life in ways you don't even realize. It dominates your life. It explains a whole bunch of stuff. We're going to spend a few days talking about all the different things that the fact that the V is squared can explain. But let's start out with a basic plug and chug. A 357 Magnum bullet weighs 8.1 grams. Do heck. I don't do physics with grams. Eric, what do I do physics with? Kilo. How do I change grams to kilograms? What does kilo stand for? Divide by 1,000. So I think you're going to get 0.0081 kilograms. 2 zeros after the decimal, 81. And travels at 490 meters per second. By the way, I looked these up. These numbers are pretty accurate. How much, kinetic energy does it possess? Jada, what's the equation for kinetic energy? Half mv squared. It's going to be 0.5 times 0.0081 times 490. Don't forget the squared. By far the most common mistake, kids write the squared, and because their brain has mentally checked that they've written the squared, they forget to hit the squared button on their calculator. Full warning, I will make fun of you if that's the case. Jada, what'd you get? I think I'm doing some really quick math. I think it's going to be in the 800s or 900s, I think, but don't quote me on that. 900, I'll just call it 972. Is that a lot of energy? You can all put out more energy than that. But that's a lot of energy for a very small area to absorb all at once. Because remember, this is also force times distance. If we absorb that in a very small distance, that's a lot of force. Enough force to penetrate your skin. And now it's going to be doing organ damage, and that's bad. But All of you have absorbed more energy than that quite casually without realizing it, just over a much longer distance, so a much smaller force. Example 5. A car has a mass of 1,000 kilograms. Sophie, what does A want me to find? Okay, let's go kinetic energy equals a half mv squared. It's going to be 0.5 times 1,000 times 5, don't forget the squared. Braden, what'd you get? Start to clue in, people. If I don't see you on your calculator, I'm coming after you. You should know this by now. I'm doing it in my head. I think I'm getting 12,500? It's half of 25,000 is what I'm getting. Yes? Units? Braden, how fast are we going in part B? How does that compare with part A? How many times faster? Are we going to get an answer twice as big? You know what? Since you all have it on your calculator, let's just backspace and change the 5 to a what? 10, don't forget the squared. Is twice as fast twice the energy? Did you get 50,000? What? Hey, can all of you do me a favor? Can you go 50,000 divided by 12,500? Take your answer from B, divide it by your answer from A. What do you get? Amelia, what'd you get? Is it 4? Huh. Scott, how fast are we going in part C? How does that compare with part A? I think 3 times faster. You want to guess how many times bigger this one's going to be? I'll give you a hint. Not 3 times bigger. That's a good, 8's a good guess. Let's find out. Let's crunch it. So it's going to be KE equals, I can bring my last 2 lines back. So I'm just going to change the 10 to a 15. And I get 112,500 joules. Can you go, Scott, all of you, answer from C divided by answer from A? What do you get? You can write a little in the margin, 9 times. So let me get this right. Twice as fast, 4 times the energy. 3 times as fast, 9 times the energy. Is there a pattern there? So, suppose an object has a kinetic energy of 5,000 joules. How much kinetic energy is required to double its speed? How many times more? Not twice as much. How many times more? And I can do that in my head. It's going to take 20,000 joules. What about if we wanted to triple its speed? How many times more energy will it take? I'll give you a hint. Not 3 and not 8. How many times more? Scott, what was it? Yeah. Has anybody spotted the pattern? What if we wanted to quadruple its speed? How many times more energy will it take? Aiden, 60. How are you getting that? Or better, instead of saying 4 times 4, if you want to say it like a math nerd and relate it to the equation and that little chant I had you do a few minutes ago, for what? Help them out, folks. Squared. It's the square of the increase. It's going to be, and now instead of writing 9, I'm going to write 4 squared times 5,000. 16 times 5,000, which I think is 80,000 joules. Remember, I said to you, this squared dominates your life in many ways you don't even realize. Here's two already. This explains why sports equipment over the past 40 years, like golf clubs, tennis rackets, hockey sticks, they've all become lighter, not heavier. Kinetic energy is a half mv squared. If I make it lighter, I'm losing a little bit with the m, but it lets me swing it faster, and I'm more than getting it back because of that squared. Who are my golfers here? Okay, what do we talk about in golf? We talk about blank head speed. What do we talk about? Club head speed. The golf clubs that you play with are far lighter than the ones that I played with when I was your age. We've realized, I know it's a bit of a trade-off. You're losing a little bit of mass, but you're more than getting it back by being able to swing faster. If you can swing twice as fast, the ball will go 4 times further. If you have the club twice as heavy, it'll only go twice as far. This also explains why it's more difficult to speed up once you already have kinetic energy. Eric, you may have noticed when you're biking, to go from 0 to, let's say, 5 meters per second doesn't require much work. But to go from 5 to 10, even though it's the same 5 meter per second increase, takes more oomph. And to go from 10 to 15 takes even more oomph. It's because of that squared. And this also explains why damage to occupants in car accidents is so dramatically different between an accident at 20 kilometers per hour and an accident at 80. What's the difference factor between 80 and 20? 4. So people in an 80 kilometer per hour accident will experience how many times more damage? Not 4 times more damage, but... And now I'm about to explain the majority of dumb car accidents. If you're going 4 times faster, it will not take you 4 times further to stop. How many times further will it take you to come to a stop? 16. You can't argue with the physics. So many drivers think, I'm going twice as fast, I'll just make sure I budget twice the distance. No, 4 times the distance, thank you very much. That squared dominates all over the place. Has a huge impact. Example 7. I like example 7. I like example 7. Example 7 is in this question. Mallory, what's example 7 asking me to find? So I'm going to go V equals question mark. I've got V's all over the place. We had V's in momentum, although that was velocity. We have VF and VI, but they gave me a mass. They gave me a kinetic energy. Is there an equation that has a kinetic energy, a mass, and a V in it? And if there is, could you read it to me, my joy? Get the V by itself. Okay. What am I going to do with the M? Which one of those is the correct answer? Going to divide the M over. Yes. So let's do that kind of on our own right now. This 2 is on the bottom, so it is dividing. So how will I move the 2 over? Technically, this 1 is multiplying. Technically, I should divide the 1. Will dividing by 1 make a difference? Oh, and then how to get rid of a squared. I'm going to have this. V equals the square root of 2 times the kinetic energy divided by the mass. If you tell me how much kinetic energy we have, I can figure out how fast we're traveling. And spoiler alert, I can figure out how fast I'm going to be going at the bottom of the roller coaster, which to me just makes it funner. So this is going to be 2 times 924.5 divided by 25. I'm going to type what's inside the square root, and then I'm going to go square root answer button on my calculator. 2 times 924.5 divided by 25, square root answer button. Mal, did you get 8.6? And units, it's a speed, meters per second. So, example 8, I like example 8, I like example 8. Example 8 is the next question. If I know how much kinetic energy my roller coaster has, I can figure out how fast it's going to be going. So, a roller coaster has a kinetic energy of 132,700 joules at the bottom of the first hill. How fast is it traveling? Claudie, what's this question wanting me to find? What did they give me? Mass? Kinetic energy. Can you look at the kinetic energy equation and can you get the V by itself? Let's see. We would divide the M, yes? What would I do with the 2 that's on the bottom? It's on the bottom, so it's dividing, so times it. And then technically, what would I do with the 1 that's on top? Technically divide it. Will dividing by 1 make a difference? No. Now that's V squared. So how to get rid of a squared? Good. I will expect you don't add that to your green sheet. The day before the test, if you're still struggling, feel free, but don't. You'll get this. And again, we don't need to memorize it. It's going to be 2 times 137,200 divided by 350, which is what? Mr. Dewick, do you actually figure out how fast you're going to be going at the bottom of the first hill? No. Why? That would be so nerdy. What'd you get? 28 what? Is that fast? Could you multiply by 3.6? How fast is that in kilometers per hour? 100. Okay. I would use this as my guideline. I'd stand in line 45 minutes, maybe an hour for a 100 kilometer per hour ride. But I've been on faster. I'm not standing in line for 2 or 3 hours. Nah. Not worth it. But this, okay. I'd give this a solid C+ roller coaster. Be pretty good. But I've been on better. Let's suppose we're designing the roller coaster and we want them to go 28 meters per second at the bottom of the first hill. How high do we need to build the first hill? Well, Maddie, can you read to me this first phrase here up to the comma? If all of the KE came from the PE.
How high is the first hill?
KE is a half little m V squared. PE is MGH. Oh, there's something kind of neat here. Is there an M in everything on the left-hand side? Say yes. Is there an M in everything on the right-hand side?
Yes.
Turns out, in this specific example, the M's cancel. Matt, have you been on a roller coaster before? Before you got on the roller coaster, did they make you step on a scale? No. Did they have to spread out heavy people and light people? No. Did they have to make sure that little kids sat next to grown-ups, that they couldn't have little kids sitting next to each other? No. Do you know why? Because it turns out on roller coasters, the masses cancel. And so if they didn't, they would have to do a lot more work. They'd have to carefully spread out all the masses and make everything all even. I don't know if you ever thought about that, but for what it's worth, that's because of that. What are we trying to find? How would you get the H by itself? How you move the G over? So you're telling me the height is going to be V squared divided by, there's going to be a 2 on the bottom from the 1/2. I'm going to divide by G. Maddie, if you want to put the 1 there for the 1/2, you can, but there is no way you can make me do that. Not happening. So it's going to be 28 squared all over 2 times 9.8. I think, I'm doing some quick math in my head, I think this might actually work out evenly. Yeah? What'd you get?
40 meters.
Okay? If I want this roller coaster to be going 28 meters per second at the bottom, that first hill has to be 40 meters high. So now we're getting into a little bit of ride engineering. We are going to pause here. However, if you want to get a head start on the homework, you're already capable of doing number 1, 2, 3, 4, 5, 6, 7, 8, and 9. You can do all of those as a head start. I'm going to finish this lesson off tomorrow, and I'll give you the rest of the homework tomorrow. But before I turn you loose,